Hello again. In this video we'll see how to use the tool to insert the data to then optimize the parameters. In the previous video we saw how to modify the models. In this one we'll see how to put it, and in the next one we'll see how to interpret it. Okay, so we can begin by running the main file that will open the tool. Okay, this is how it looks when you open it. The first three buttons are to open and save the data that you put in the tool, because it takes some time to put all this data. It makes more sense to, once you finish it, to just save it and open it later on if you want to do changes. Okay, the next buttons are used to run and stop the simulation. The one in the middle is to update the graphs if you have them to not update automatically. You have to understand that it may take a few minutes, up to a few minutes, to stop a simulation, because you cannot just stop it right away. You have to finish the current iteration. Okay, the next buttons control different sections of the application. You have data tab, which is the one you're seeing now. Then you have convergence tab, where you can see the evolution of the parameters over time. We're still in the data tab. You can actually put the data here using some format that I have created, but it's a bit complicated, so it makes more sense, as you will see later, to click in the wizard button on the bottom, and you'll be able to just use a very simple GUI to put all the information you need, and then put it back here without having to use these codes. Okay, this is the convergence tabs now. Convergence tab, where you will see the evolution of the parameters over time, as well as the error. But right now, because there's no simulation being run, you are not seeing anything. Okay, third one is result tab. Here you will see comparison between your model and the experimental data. It's nice to have a visual way to compare how well your current optimization is doing, and you have all the data in the convergence tab that this result tab can provide a better, more intuitive way to see the results. Okay, you have to put this is settings tab. It's very important. You have to change the locations of where you have PSpice installed. You actually have to put the exact location of a file called psp._cmd. The easiest way to find, if you don't know where it is, it's just where you have PSpice installed, but you can just look for PSpice, right click, open file location. Then within the shortcut, you right click, open file location again, and this is the folder where PSpice is currently installed, and also is the same folder where psp_cmd is, as you can see. So just copy the folder and paste it here, or not /psp_cmd.x at the end, and you're ready to go. Last, you can change also, if you want to auto update graphs. It can improve performance, but usually because models are slow in PSpice, it doesn't really matter, so just leave it on. Here's the help that you can access with the last button. Like, everything I'm seeing is here. If you have any doubts, try to find it here. If it's not here, or you have found a web bug, you can just report it in the website. Okay, and lastly, you have the buttons to control the graphs. Okay, so let's begin by putting the data. Remember, we had two models, a static one, a dynamic one. We'll have to put the data for both of them. So we use the wizard since it's easier. We open it here. We have all the tabs with all the different parts: lab data, model data, parameters to estimate, and more. Okay, so you basically change the different tabs to put different data, and you use the plus and minus buttons to add entries to the different data. Here in the lab tab, we'll put the data related to the experimental data we have either measured or gotten from the manufacturer website. Okay, so in this particular case, if you remember, we have a static response, and we have to plot current in the collector versus voltage in the collector. we have a txt file that we got from a PDF taking the points by hand, and we're just going to plot it now to see exactly what we are having. But the way you do is you put a txt file separated by spaces of the data. So in this particular case we have two columns where the first one is, if I remember correctly, is voltage, and the second one is the current. So we just plot it in MATLAB just to be sure you don't need to do this. So yes, we could, as we can see, first one is voltage, second one is current, as we wanted. So we have to remember this because it's very important, the order. First one voltage, second one current. Okay, so let's select the data file. Now that we are sure what there is in it, we select it, and then okay. We have to put what number in what column is the x variable and what column is the y variable. X variable in this case is the voltage, which in this particular txt file is the first column. So we'll put 1 in x. As you can see, first one is voltage, second current. So we put 1 as x, and in y we put 2 as the second column is the current, which is the y variable in the plot, as you can see. So let's do that. Okay, last but not least, we have to put the margins. We have to say from what point to what point the x-axis we want to use the data, because some points may not sense or whatever. Like, you always have to put the limits. So we have to select some limits that contain the data that we actually want to use. Everything that you will see later on in the optimization tool in the graphs is everything the program has access to. So we have to limit the access to the data that makes sense or we want to use. So in this case we could use between 0 and for example around 2.5 something as limits in the x-axis, since that's the voltage and we can see in the graph where's the limit. In the model we have a DC sweep that goes up to 7 volts, so there's no problem there. So we'll put the limit, something that contains the data and looks okay. And then last we have to put the number of points. You'll pick a number of points between those limits. It will get the points evenly, and if that particular point is not in the data set, as it will probably not be, what the program will do will just interpolate linearly. This is interesting because, for example, if you have a curve that in a particular point is linear, when you create, if you get the data, for example, from a dataset and you are taking the data by hand, you have to understand that you only need 2 points, since the optimizer tool will automatically interpolate the missing points, and since it's aligned, the interpolation will be perfect. Okay, we also have to put the name. Just put the name you want to see later on, so you can see exactly what you're plotting. In this case, let's put something like the gate voltage and the temperature we are using. Then we can go to the model tab and add the model data. And there's one thing you have to know, that we got an error now, because let's not say it's a problem, but it is with MATLAB, that if you change the directory and you didn't add it to the path, the tool may give you an error, but it happens with any MATLAB application. What you can do is just add it to the path, or if you have this problem, just run it again. And so you change the directory back to where the tool is installed. Okay, so in this tab you can put the models. What we'll do now is we'll pick the model, the CIR file that contains the test that will be compared with the first curve in the lab, the tab, which we were using a static one, so we'll pick the static model. Then we have the op parameter which is options. Yes, leave it blank. Most of the times you will not need to change it, but it's small modifications that you can do in the algorithm of the way it treats data. You can see what options you can put in help, but in most cases you don't have to do anything, so just leave it blank. Then again, you have to select what x and y variable you want to use. So if you remember from before, in the previous video, when we ran at first the CIR file for the static test, we put the print statement and we saved a number of variables, and we said you have to remember which variable you save and what's the order. We can open the old file again, and you see like first one was voltage in the collector, second one is the current through the collector. So because you want to plot current versus current in the y-axis and the x-axis the voltage, you would put 1, 2, because the x-axis is directly the voltage, which is the first column, and the second column is the current, which is the y-axis. Okay, now we have to put the parameters. I'll just open the CIR file because servers don't even remember how many parameters they have. So what you do is, again, you just press the plus button, you add as many as you want. If you want to remove parameters, curves, or whatever, you just have to use the minus button, and you can also change the by changing the end. If you put the number of it lies in the list, you can delete or add after that that element in particular. So I'll just put you put in each parameter the name. It's you have to follow the same as MATLAB variable names, and then you put the initial value that you will use. You try to put a value as good as you can, like it will always help the optimization to have a value close to the real one. Like you cannot expect to put 1000 in something that's expected to be 1 to the power of minus 10 and it to work. It may work, but it's not a good practice. Just try to put the closest value you can. Okay. And then you also have to put minimum and maximum values that that particular parameter can change. This will help the algorithm. So try to be as good as possible, putting both the initial guess and the limits of each parameter. Now it's just a matter of putting all the rest of the parameters. So I will just put them. I will pause the video, skip this, and I will continue after I have them all. You just have to follow again the same order that you have in the CIR file. So if you remember, for example, T2 was the first parameter because you said T2 equal bar param 1, and so the rest of the parameters will follow the same. Okay, here we are again with all the parameters already set. Have to, as I said, you have to follow the same order you chose arbitrary in your simulations. So you can see the first parameter is T2, as you said before, T2 equal bar param 1, and so on with the rest of them. And now what another thing I also want to explain is not really that important, but it's worth to know, that if you have parameters that you expect to vary a lot in order of magnitudes, like then it can be a good idea to perform a logarithm transformation to improve results. Not to improve results, but more like to decrease the time it takes for the optimizer to find the right parameters. So if you want to do a logarithmic transformation, you just have to put in the parameter, you put the name you want under underscore log, and the tool will automatically understand that these parameters needs to be logarithm transformed. Okay, we move to the more tab, or you can put the constraints and select the optimization method. One thing also that is important is to don't mix constraints that with parameters that are linear. Has been linearly transformed, which are the default ones, and with the ones that logarithm transformations have been applied. So for example, for this problem, let's put like just an example. So let's put 3 different constraints. We'll remove them later because we don't really need them, but just as an example. So what you do is you simply type the names of the constraints. You put, for example, here we are going to say the sum of gammas is, for example, sum of gammas is equal to some value or less or than equal than some value. You would just do so by typing the variables and putting like summing them, and then it's important to know that the variables have to be always on the left, and on the right you have to put the constants. You can put linear constraints. What this means is that you can multiply or divide each parameter you want by a constant, but you cannot, for example, multiply parameters. You cannot apply I don't know, functions like sine, cosine, and so on. But in most cases this is all you need. So try to find a way to put it in with a linear constraint. Okay, here we'll just put as an example the three different type of constraints. You can put something is equal to something, something is less or equal to something, or something is more or equal to something. It's important to note it's semantics, but the way the tool is designed, you cannot put this less than or more than. You have to put less or equal to and more or equal to. Just keep that in mind when you put the constraints, otherwise it will give you an error. So here we have the three example constraints, and we're just going to remove them because they were examples, but we don't really want them in our model, so we'll remove them. Okay, now what you have to do is select the solver you want to use. There are three different ones I have added, and they are just program in the MATLAB optimization toolbox. You have to understand like the basics of how optimization works. So the way it does is you have, let's say, two big groups of algorithms. You have gradient-based algorithms, and then you have another set of algorithms that just use some kind of heuristics. So gradient-based algorithms are always the fastest and the best as long as they work, let's say. What they do is they try to go in the path that minimize the error, and they do so by making small changes in each parameter and seeing the effect in the error. So that way they can estimate the gradient of error over error change over parameter change, and use that information to choose a path to move. And as I said, they are the fastest one because it makes sense like to do something like this. But on the other hand, the problem with them is you have to choose between fmin_con or global search. First one is a local optimization algorithm. This means that you put a set of points, and the solution you will get is greatly affected by the initial guess. Because if you have a problem with more than one minimum, what you will do with this method is you will find usually the closest minimum, which may or may not be the global minimum. What this means is that the solution you find will be a minimum for sure, but it may be a local minimum, which means that you may still improve your solution if you were to use another solver. For this reason, you may use a global search to try to find for the global minimum, which would be the best solution you could get. But again, the problem here is that there's really no way to guarantee that you have found a global minimum. It's simply impossible. Let's imagine, for example, you are in a surface blindfolded, and you just try to find, for example, the highest mountain. The only way you can be totally sure you have found the peak of the surface, if you cannot see, is to just go through the whole surface, which from an optimization point of view would not be efficient at all. So you always have to apply some kind of logics to try to guide you in the best direction you can find, but this will not guarantee you will get the best response. For this reason, a part of global search I have also had a genetic algorithm, which it uses a heuristic that mimics evolution. What it does is it creates a lot of initial points, and it somehow tries to find tries to combine the best ones all the time to create, let's say, another set of points and so on. It's like it would pick the parents, and then the parents would pick children based on the qualities of the parents, and it's more likely to pick better parents than worse parents and so on. It also induces mutations, and so it tries to also like suddenly change parameters so it doesn't get stuck and so on. But again, it's heuristic. It will not guarantee you will find the global minimum. And the problem with this method is it is really slow. It's much slower than both fmincon and global search. But the advantage is that it's more generic. So if you have a really complicated problem where you have, for example, discrete variables, or your functions are not defined in some points, genetic algorithm may be the way to go, since the other two will not simply will not work. Okay. So from all this general explanation about these three methods, my suggestion would be that you should start with fmincon, and somehow it would be a good idea to try to come with a way to get the best initial guesses. But that's just try to do that, but it's not always easy. If fmincon doesn't work because the solution you get is really bad, try global search. And if finally, if your problem cannot be solved by these solvers, you can just use genetic algorithm. And now let's move. Let's continue adding. If you remember, there was another simulation file, a dynamic test. Let's first start by adding experimental data. So we go to the laptop, we press plus in corp, and we select the txt file that contains the data. This data we have measured it in the lab, and it's using the same IGBT as the one that had the static test. Let's try to plot the data to see exactly what we have. Again, the data has to be in a txt file where each column has each column is a different variable. Okay. So as I said, it has to have each column for a different variable. First one is time. Second one is voltage in the collector, and third one is current in the collector. It should be. Let's try to plot it to see if that's what it is. Again, data has to be separated by commas. By spaces, as you can see in the txt file. Okay, so let's try to plot the data. Okay, let's plot first column as the x variable and the second column as the second variable, and let's see if what we get is the voltage over time as we would expect. And here we go. Yeah, we get voltage over time. Now let's see third column as the y-axis. We should get current, and here it is the current, the collector over time as it should be. So this is just showing you this so you understand better what I'm putting later on in the tool. It's important to note because this is a this simulation uses time. We had to synchronize the time in the simulation and in the experiment. We did so simply by choosing that the gate signal that is being given to the experiment and the model is made arbitrary at the same time. So we basically shifted this txt data has been shifted in such a way that those times coincide between model and experiment. Okay, so now that we've seen in the figure what we had in the txt file, just to be sure, we'll put the data the same way as we did before. We're going to plot first the voltage because we want to do so, it doesn't matter. So the x variable is the time, is the first column as we saw in the txt file and in the plot. And the y variable is the voltage, is the second column, so we just put the 2 here. Then again, we have to set the axis limits of the x-axis, which is time in this case, and we'll just set the limits in such a way that we get we're interested in the transient response. So we definitely want to have this part where the voltage goes up and this part where the current goes down, but we also want to have a little bit extra for several reasons. For example, when the initial parameters are set, your course may be a bit behind or after model and experimental data may be shifted a lot, and if you take a really small segment, it may be hard to optimize. And also on the other hand, later on, if you have a really small segment only with the transient, maybe the steady state part is also wrong, so it's also a good idea to, in a way, include a little bit of the steady state part. But those are just advices that may change depending on the project. So let's pick the time, number of samples. Let's pick 100 is okay. Again, it doesn't really matter that much. Let's put name voltage. Now we can put press plus to create a new curve for the current, but it's interesting, this is not really needed. We can just press subcurve and it will you can add another curve using the same txt file. In this case we want to put current, so first is the time, is x variable is 1, current was the third column, so y variable is 3. Now we put the time again, more or less. We want the transient and a bit more before and after. We'll put, for example, this. Number of samples 100, for example, is okay. Name, for example, current. Okay, now we can move to the models tab, and we'll add the models that will be compared against the experimental data. Models and experimental data are compared as pairs one by one. So the first experiment will be compared with the first model, the second experiment with the second model, because we have in the same model and experiment different subcurves. The second curve in the second experiment will be compared with the third element in the models, which would be the second element in the second model. Basically, they are compared in order, and everything will work fine. So again, we pick the SIR file for the dynamic response. That will be compared against this experimental data for the dynamic one. And now let's fill this rest of the data. We can put another subcurve because we want voltage and current, and they are both in the same SIR file. Otherwise, we'd need to put another curve with the corresponding SIR file. So let's check again what we had in the SIR file, just to make sure, like we saw it in the previous video, but just to remember. First column is time, second voltage, third current, the collector, which by chance is the same one as we have in the experiment. Anyway, so we want to plot the voltage first and then the current too. So voltage and voltage is compared, and current is compared. So x axis is 1, y axis is 2 as it's the voltage. Sorry, y axis is 2 as it's the voltage. And first column this time we'll put it in the second model, and the current is the third one that we'll put in the y variable. So voltage and voltage compare, current is compare, and you will be able to see later when you run the tool, everything is fine, you will see it makes sense. Again, here we have the parameters. Constraints, we remove them all, we didn't really want it. You can check algorithm SFMinCon as suggested. Again, if you have any doubt, you can just open the help, and most of the information is there. It should be there. If there's something that is not clear, just go to the website and comment there. Okay, so now we'll just save the file. Let's call this a configuration file. We'll put any name. It will save a txt file that you can open again from this wizard and see all the data. And then you will also use this txt file in the optimization tool. So now you just press open, and you will open the configuration file that you have just saved with the wizard. So here's all the data. You could have put this data by hand in the tool. It would have worked. It's not a problem, but I think it's just easier to use the wizard, as you are just using a GUI pressing buttons. You can open it again from the wizard. You see, you have there all the data. So the whole problem has been assigned. You have modified the models. You have put all the data in the tool, and now you will be able to just press run, wait, and hopefully you'll get good results. Thank you for your time.